Welcome to the Explainer. Now look, if you think trigonometry is just some dry, boring set of formulas designed to torture high school students, I want you to completely wipe that slate clean right now. Today, we're looking at the fundamental language of the universe. We are literally going to decode the very patterns that govern everything, from the incredible structures we build all the way to the waves of light we see. Okay, let's dive right into this. And honestly, this image brilliantly illustrates exactly what I mean. Take a look at the majestic Chichen Itza pyramid. Think about it. How did its ancient builders calculate the exact angle of those massive sloping sides? Well, over 400 years ago, Galileo Galilei said that the laws of nature are written in the language of mathematics, and its symbols are triangles, circles, and other geometrical figures. Without these shapes, it's just impossible to comprehend a single word of nature's book. Trigonometry gives us the key to actually read that book. So the crucial takeaway here is that by mastering these shapes, we're basically mastering the source code of reality itself. So, here is our roadmap for today's explainer. First, the language of triangles. Second, beyond 90 degrees. Third, reciprocals and infinite waves. Fourth, transforming the graphs. And finally, number 5, equations versus identities. All right, let's start with block number 1, the language of triangles. We're just rewinding briefly to the fundamental rules that govern right-angled triangles for angles between 0 and 90 degrees. Okay, here are our core definitions neatly packaged up. SOHTOA, it's an abbreviation you probably remember, but I promise you it is absolute bedrock. For any given angle, which we usually denote by the Greek letter theta, the sine is simply the ratio of the opposite side over the hypotenuse. Cosine is the adjacent side over the hypotenuse, and tangent is opposite over adjacent. You've got to lock these 3 ratios into your mind because they are the foundation for absolutely everything that follows. Now, certain angles pop up so incredibly often in math that knowing their exact values in fractions and surds, rather than relying on those messy calculator decimals, is, practically speaking, a superpower. For instance, the sine of 30 degrees, or pi over 6 in radians, is exactly 1/2. The sine of 60 degrees is root 3 over 2, and the tangent of 45 degrees is perfectly 1. Knowing these exact forms allows you to maneuver through complex, high-level problems with absolute precision. But here is where we hit a bit of a wall. Right-angle triangles only allow for angles up to 90 degrees, right? So what happens when an angle is larger than that? Let's get into block 2, beyond 90 degrees. To measure angles of any size, we just place our angle inside a unit circle on the xy plane. Suddenly, our angle can sweep around infinitely. But because x and y coordinates can be negative depending on where you are on the plane, the signs of our trig functions are going to change. To track this, we use something called the cast rule. In the first quadrant, all functions are positive. In the second, only sine is positive. In the third, only tangent. And in the fourth quadrant, only cosine is positive. If you start from the bottom right and move counterclockwise, it spells out CAST. It's a really simple rule, but it lets you evaluate angles of literally any magnitude. Now, if we take that sweeping circular motion and unroll it over time, we discover something genuinely beautiful. Let's look at section 3, reciprocals and infinite waves. Before we actually look at the waves themselves, we need to meet 3 new mathematical alter egos. Alongside our familiar core functions of sine, cosine, and tangent, we have their reciprocals. Let's map them out. The reciprocal of sine, meaning 1 divided by sine, is called cosecant. 1 over cosine is secant, and 1 over tangent is cotangent. And here's a really cool detail. Whenever sine hits 0, cosecant becomes undefined, which creates these fascinating vertical asymptotes in their graphs. When we plot these functions out, they create continuous, repeating waves. To really understand them, we need to know 2 vital pieces of their anatomy. First up is the amplitude. This is the largest vertical displacement from the central horizontal axis. You can just think of it as the height of the wave. Second is the period, which is the horizontal interval it takes for one complete oscillation before the wave starts repeating itself. For sine and cosine, that period is 360 degrees or 2 pi radians. For tangent, it's a bit tighter at 180 degrees. Once we understand the basic anatomy of these waves, we actually gain the power to manipulate them. And that brings us perfectly to section 4, transforming the graphs. Let's break down this somewhat intimidating formula. Y equals A times the sine of bx plus c. I know it looks a bit complex, but it's really just a straightforward set of instructions for a visual transformation. Step 1. The letter A stretches the wave parallel to the y-axis. It's directly changing your amplitude. Step 2. The letter B stretches or squeezes the wave along the x-axis by a factor of 1 over b, which changes its period.
And finally, step 3, the letter C translates the entire wave vertically, shifting it up or down. And listen, this is a crucial detail to remember. When you are drawing these transformations out, that vertical translation step must always happen last. We have finally arrived at our last building block. We know the functions, we know the waves, and we know how to transform them. Now we must understand how to use them logically. Let's jump into section 5, equations versus identities. There is a critical distinction in mathematics that we really need to get straight. An equation is kind of like a question asking, hey, when does this wave hit this specific height? For example, the equation tan theta equals 1 is only true for specific values, like 45 degrees or 225 degrees. By contrast, an identity is a universal truth. It is true for absolutely all values of the variable. For instance, tan theta is always equal to sine theta divided by cosine theta. That is a fundamental law of mathematics, and we even use a special 3-line equal sign just to denote it. And building right from that fundamental truth, by applying Pythagoras' theorem to the unit circle, we derive what are essentially the ultimate mathematical cheat codes, the Pythagorean identities. First up, sine squared plus cosine squared is identically equal to 1. Now, if we divide that entire equation by cosine squared, we get our second identity, secant squared equals 1 plus tangent squared. And if we divide the first one by sine squared, we get the third. Cosecant squared equals 1 plus cotangent squared. Look, whenever you face a really complex algebraic proof, actively looking for ways to substitute these identities is exactly how you simplify the impossible into the solvable. Wow, okay, we've covered a massive amount of ground today, from the basic ratios of a triangle's sides to the infinite transforming waves of advanced identities. But I want to leave you with a thought before we go. We started with the physical slope of a stone pyramid at Chichen Itza, but where else in nature do we see these exact same oscillating periodic patterns? Well, the answer is literally everywhere. The tides of the ocean, the swing of a pendulum, the alternating current powering the screen you're looking at right now, and even the sound waves carrying my voice to your ears, they are all governed by the exact same trigonometric functions we just decoded. You now hold the Rosetta Stone. The only question is, what patterns in the world are you going to decode next? Oh, and if you're using this to master your math exams, definitely subscribe to our YouTube channel, AC Exams at acexams_IGCSE to excel in your Cambridge examinations. Thanks for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.